In this lesson, we're going to take a look at Newton's third law, which is different than his first two. Newton's first law, as you recall, said in objects, velocity remains constant unless it's acted upon by an unbalanced force. So we were talking about one object. Newton's second law is the equation net force equals mass times acceleration. That's the net force acting on a single object. It causes that object to accelerate. Depending on how big its mass is, its acceleration will be different as well. Again, we're dealing with one object. Newton's third law is different. Newton's third law deals with two objects, and it's important that you recognize that. Newton's third law simply states that when one object exerts a force on a second object, the second object exerts an equal force back. On the first object. That's two distinct objects. I have object 1 and object 2, and whenever two objects interact, whenever two objects collide or push each other, they always push each other with the same amount of force, but those forces act on different objects. And so there's this classic problem where we have a wagon hooked to a horse. This is going to be awesome. Here's my horse. Got to have a mane, some feet, and a tail. All right. And so we say to the horse, hey, pull my wagon. And the horse says, no. No matter how hard I pull the wagon, there will be an equal and opposite force back. And so I will never get to go anywhere because the forces are always balanced and therefore no acceleration can occur and the wagon has to remain at rest. Now we know that that's not true, but where's the fallacy? What mistake is being made there? Well, it gets down to what forces are acting where. This force right here, that force is acting on the cart. That's the force the horse exerts. So I'm going to say F from the horse. That force is only got to overcome friction, right? So this ground, there's ground sitting here, and there is a frictional force against that motion. And as long as that frictional force is smaller than the force the horse applies, then the cart can be accelerated. Right? Now, what is the horse actually pushing on? Well, the horse is pushing backwards on the ground, right? And because of that, the ground pushes forwards on the horse. So this force right here that the horse exerts is actually acting on the ground, and then the ground exerts a force back on the horse. Those two forces are also equal and opposite. Of course, the ground is the planet Earth, so that force is not going to cause much of an acceleration, and the reaction force acting on the horse causes the horse to accelerate forward. So we have multiple forces acting on things, but this force backwards on the horse from the cart has to be smaller than the force that the horse can exert on the ground. And so as long as we can overcome this frictional force, then this thing can be put in motion. So Newton's third law says these forces act on different objects, and it's important that you remember that, because it is true that the force that the cart puts on the horse is equal and opposite to the force the horse puts on the cart, but those two forces act on different objects. So it doesn't matter that they're the same. They can't balance. They're on different objects. And so the classic problems that we have here are things like, hey, suppose two bumper cars hit, two cars. I've got one that has a mass of 50 kilograms and it's moving this way. And I've got another one that has a mass of 100 kilograms and it's moving this way. And if they hit and collide, say this one goes from moving at 2 meters per second to, well, it would be negative to the left, to 0 meters per second, and it takes 0.5 seconds for this collision to occur. I want to know if this thing was initially moving at 3 meters per second, how fast is it moving after the collision? And we are going to assume that we can ignore any frictional forces. The only forces we are looking at are the forces that are acting on the two cars from the collision. So the first thing we're going to do is figure out So what I want to know is, what's our final velocity? Question. First thing we have to do is figure out what forces we're acting, right? Because if we're going to get our final velocity, we need to know about acceleration. If we want to know about acceleration, we have to know about time. And so to do that, I have to look at this cart, because I know that this cart is going to get pushed this way. This is going to be, if this is 1 and this is 2, this is going to be the force from car 1. But there will be an equal and opposite force on this car, the force from car 2. Those two forces are equal in size, opposite in direction, and act on each other on different carts. And so this is now just a Newton's second law problem, right? As soon as I've established that these forces are equal and opposite, then all I've got left to do is the math. And so here I can say, well, F equals ma, and so final velocity 0 minus initial velocity -2 equals 2. Divide that by 0.5, acceleration equals 2 divided by 0.5, which equals 4 meters per second, and I can multiply that by 100, so I get 100 times 4 equals 400 newtons. So this 400 newtons was acting to the right, which means now I have a negative 400 newton force acting over here. Newton's third law tells us that's there. And so now net force equals mass times acceleration, and so negative 400 equals 50 times the acceleration, and the acceleration equals -8 meters per second. And so if that acts for 0.5 seconds, V equals V naught plus AT, so 3 plus -8 times 0.5 equals -1 meter per second, or just meter per second. That's our final velocity. So we know after these two things collide, the bigger cart stopped, and the smaller cart is actually moving the other direction now at 1 meter per second.